Have you heard about the amazing news from Igor Mordach, the Google DeepMind's researcher, about his team? They used AI to control an electron microscope to rearrange individual atoms. Yes, the mystery silicon dopant transitions in graphene. Today we dive deep into the fascinating world of atomic manipulation inspired by Igor Mordach's intriguing post on Twitter. Our focus is on the movement of silicon atoms across a one-atom-thick layer of carbon, also known as graphene. Let's unravel the enigma that Mordach has piqued our interest in. A groundbreaking development, the machine learning approach, has been introduced to determine the transition dynamics of silicon atoms. This method is data-centric, revolving around the use of a scanning transmission electron microscope, or STEM, to collect vital data. In the heart of this process, the STEM stimulates the silicon atoms, causing them to move across the graphene layer. This movement is recorded and transformed into a series of data samples. These samples are then processed and filtered meticulously to produce symbolic representations. But what do we do with these symbolic depictions? They act as a valuable wellspring of data for refining our next crucial component, the neural network. This neural network, adorned with complex layers of synthetic neurons, is engineered to predict transition probabilities. To put it in layman's terms, it anticipates the potential movements of the silicon atoms. We are absolutely thrilled to share our latest endeavor that employs AI to manipulate an electron microscope for rearranging individual atoms. This has been an incredibly enjoyable collaborative effort between @Google DeepMind, @Mila_Quebec, and @ORNL. Having control over matter at the singular atom level could be an immensely potent capability. Humans can manage this through meticulous manual control of an electron microscope, but AI can automate this procedure, enhancing efficiency and reducing errors. Our focus was on shifting silicon atoms in graphene, a single atom-thick arrangement of carbons. Through illuminating with an electron microscope beam, we can momentarily displace the silicon and have it swap places with a carbon atom. The electron beam needs to be placed at a specific location and intensity, a problem we solve using model-based control methods. Once the neural network has been trained effectively, it doesn't just predict, it guides. It leverages the learned transition dynamics to navigate a single silicon atom throughout the graphene lattice. The destination isn't random, it's predetermined, showcasing the precision and control of this innovative approach. But how effective is this method? Empirical analyses have been conducted to answer this very question. The results shed light on the efficacy and generality of this approach. It's not just about theory, it's about practical application and real-world impact. In summary, the machine learning approach to silicon dopant transitions in graphene revolutionizes how we understand and control atomic movement. It begins with the collection of data through a STEM, which is processed to create symbolic representations. These representations train a neural network to predict and control the movement of silicon atoms across a graphene layer. This journey from data collection to atomic control is a testament to the power of machine learning. It's a blend of technology and science, a convergence of data, artificial intelligence, and atomic physics, pushing the boundaries of what we thought was possible. It's not just about observing the atomic world, it's about interacting with it, controlling it, and ultimately learning from it. So the next time you think of silicon dopant transitions in graphene, remember this machine learning approach. It's a window into the atomic world, a bridge between data and physics, and a step towards a future where we can manipulate atoms with precision and predictability.
Enjoyed your journey into the AI Future Hub? Support us by click subscribe, hit like, share it around. Keep the future at your fingertips. Loop in, don't miss out.